Well, friends of mathematics, we're finding ourselves talking about Math 105, section 4.1, and we need to introduce exponential functions. And in order to even think about talking about exponential functions in general, we should probably talk about exponential rules first. Now, I'm not here to explain these rules to you. I just need to put them out there so that we don't make a mockery of mathematics when we begin to play this game. So if I have x raised to the a times x raised to the b, we're going to have x to the a plus b. Similarly, if I have x to the a, and I raise that to the b power, now we're going to multiply our exponents. I guess I could say that if I have x times y raised to the a, that this distributes through x to the a times y to the a. I could say the exact same thing is true for x divided by y raised to the a power. And I guess we could probably talk about x to the negative a as 1 over x to the a. And I guess I can include if I have x to the a divided by x to the b, we'll have x to the a minus b. But I think that's really a combination of rule number 1 and rule number 2, or rule number 4. Suppose your salary increases by 3% each year. So let's just have S naught as your starting salary. And let's call that 3% the interest rate. How about yearly rate of growth? So what am I going to do with S naught? Well, I can take S naught and I can add it to that 3% times S naught, but there's a better way of combining these two, right? I could factor that S naught out, and we refer to 1.03 as our growth factor. Usually we're going to use the letter B to describe our growth factor, which is 1.03. And so if I did this for, this is just 1 year, if I did this for the next year or the next year, I can say that my salary as a function of t years is going to be equal to S naught times 1.03 raised to the t. So in year 0, we can see that we'll have S naught times 1.03 raised to the 0, and that's going to be equal to 1, and so we just get our initial salary back. In general, an exponential will be of the form f of t is equal to a times b to the t, where we refer to a as our initial, b is our growth factor, and we use the term factor, meaning that we're going to be multiplying by this b value every single time, and r is our growth rate. Now, mind you, a growth rate can either be a positive or a negative value. But if I'm talking about a decay rate, I'm only going to want to discuss this in a positive way. So if I had something like this, g of x was equal to 3.1 times 0.9 raised to the x, we can see that 3.1 is equal to a, that 0.9 is equal to b, that 1 plus r is equal to b, and we get that 0.9, and we can subtract, and we can see that r is equal to negative 0.1. But I could say that this is 10%, I'm sorry, negative 10% growth, or 10% decay. And, you know, 10% decay is probably the preferred way to discuss this thing. I need to do one last thing, and the reason I left these rules here is a lot of the times we're going to get some exponential and we're going to have to manipulate it to put it into the form ab to the t. So if I have something like this, let's say h of t is equal to 3.1 times 0.9 raised to the 2t plus 1. And I want to get this in the form of a b to the t. And so what we're going to have to do here is we're going to have to use our properties of exponents to manipulate it to get it into that form. And the first thing I might do is I might split this thing up with that first property. So we'll have 3.1, 0.9 to the 2t times 0.9 to the first. And you can see that what we did is we went this way with our rule. I can pretty much see what a is right now, and I could have seen a before because our initial value, when I put 0 in, everything murders except for the 3.1 and the 0.9. So a is certainly equal to 3.1 times 0.9. But now to figure out what b is the value that's being raised to the t power. And so what I'm going to do is I'm going to undo this second property, 0.9, or so I'm going to undo it. So 0.9 to the second power, all of which will be raised to the t. So I can keep that 3.1 and that 0.9 equals h of t, and we're done. b is equal to 0.9 squared. The final thing that I might be asked to do, and notice that 0.9 squared is going to be 0.81, and so this is going to be a decay problem. So what is the exact percent growth rate? Now, percent growth rate, that's definitely an R question. And so we know that B is equal to 1 plus R. And we have that 0.9 squared, which is awesome. 0.9 squared is equal to 1 plus R. And we can get, so we'll have 0.9 squared minus 1 is equal to R. Unfortunately, this value right here is not written as a percentage. And so we'll multiply by 100. But there's a problem here. If I was to punch this in, remember that 0.9 squared? That's going to be a negative, or that's going to be a 0.81, and so when I subtract 1, and so this is, oh, I guess I did answer the question. The exact percent growth rate is this. If I was asked for the exact percent decay rate, I would have to take this value and multiply it by a negative 1, because a decay rate is always going to be a positive value.